Greetings and welcome, friends. We're talking about writing equations of hyperbolas today, in which we're going to kind of get some clues and be able to find the equation. It's kind of you guys are a little bit used to this concept already. We did it with circles, we did it with ellipses. But before I get into that, I actually want to talk about a special kind of hyperbola, which is called a rectangular hyperbola. And rectangular hyperbolas are hyperbolas that have been rotated kind of like 45 degrees, I guess. And they are of this form. They are of the form, let's see, I'm getting a little bit of lag here. They're of the form x, y equals c. So this is the first time we've had an xy term, right? We've had x squared, we've had y squared, we've had x, we've had y, we've had a constant. But now I've got an xy term equaling c. And it turns out, depending on the value of c, you can tell, well actually let me draw a quick example of what this would look like. So the graph of it, actually I might just use a couple two-color situation here. If c is positive, the graph looks like this, where your asymptotes are actually the x and y axes. Like that. And then your vertices are right there and right there. So it kind of lines up perfectly with the coordinate plane, I guess. And then in the case of, let's see, let's get another color here. No, can't be green. Maybe I'll use the light blue. Sure. If c is negative, then it happens to land in quadrants 2 and 4. Yeah, I guess, yeah, having two colors for this would be good for your notes. Or you could just draw two sketches, I suppose. So these are rectangular hyperbolas. By the way, the idea of a square hyperbola, or equilateral hyperbola, sorry, is one in which the slopes of your asymptotes, both a and b are equal, I guess, is what I'd say. And the slopes of your asymptotes are therefore plus or minus 1, is what you end up getting. So these ones are kind of equilateral hyperbolas in that sense, where our little boxes would actually be squares that form the asymptotes there. But that's the idea there. And there's also a way you can find your vertices. I guess this is my own little trick. The vertices are going to be, well, let's actually think about this one. Maybe I should have fit it up there, but it's going to be related to the square root of c. Is how you can find your vertices for these. So for instance, this point right here would be square root of c comma square root of c. This point right here would be negative square root of c comma negative square root of c. And then this one is positive root c, and you can kind of figure it out from there. But they're all just related to the square root of c because they end up kind of having to make this equation true. And the x and y coordinates for all of these, well, for the vertices anyway, sorry, are equal. So that's kind of how that one ends up working out. Or they're at least equidistant from their corresponding axes. So yeah, this one would be square root of c comma negative square root of c. And this one would be negative square root of c comma positive square root of c. So as long as you remember which quadrants this lands in, so this is quadrants 1 and 3. This was quadrants 2 and 4. And we'll be more familiar with the quadrant labelings later on when we're doing some trigonometry. But they start in the positive quadrant and go counterclockwise. So that's how you'd label your quadrants. So that's a sad looking 4. Yeah. Draw the curve?
Yes.
Yes. Yeah, I would recommend that because it is possible I could have one that's like really close, or I could have one that's like really far away. So your vertex is going to be the point that helps you know kind of where that's landing. Also, you may have seen this before. I think in Math 3. I guess, yeah, just let me do a quick little recall concept. If I have the equation xy equals c, and I solve that for y, dividing both sides by x, I end up with a rational equation. So y equals c over x, which is a rational equation. And we used to graph those back in the day with vertical and horizontal asymptotes. So we used to actually have some experience with that. If I recall, I think we spent a little bit of time graphing those where we'd find the asymptotes and everything. In this case, for these hyperbolas, the asymptotes happen to land exactly on the, x and y axes. So that's the first idea regarding rectangular hyperbolas there. So those are kind of an interesting case. You'll just have a couple of those show up on homework tonight. Let's see, the other thing I want to talk about is eccentricity again. Fortunately, it's defined as being the same thing. It's still the ratio of C over A, and it's still between 0 and 1. And I'll just draw, well, maybe I'll just show you this picture from the book real quick if it's not blurry. Oh, it isn't blurry. Hey, congratulations, book. Just to give you an idea of what an eccentric hyperbola is, because it's not necessarily completely obvious. Oh, wait, actually, wait a minute. Aha, I might have made a mistake right here. Man, my bad. Right, because, well, in this case, C is bigger than A. So C over A. Yeah, aha, I messed up, guys. My bad. Forgive me. My apologies, friends. In this case, it's actually going to be kind of the opposite. C is just going to be bigger than 1. C over A. Because C is always bigger than A in the case, right? So C, the focus would be here, your vertex would be here, this distance is going to be bigger than that in the case of hyperbola. My bad. So if it's close to 1, like 9/8 they're saying, you've got kind of the one that is, more vertically stretched, I guess, in this case. And then if it's further from 1, like 13/5 or something, then it gets more exaggerated this way. So I don't know how you'd want to describe that. If you'd want to describe, this is skinny, I don't know. I don't have a good word to visually describe that necessarily. Oh, not necessarily. As long as you understand that it's the same value to calculate eccentricity as C over A, is what we'd end up doing. So we'll just have some problems with clues about it. I guess this is kind of stretched this way, and this one is kind of smooshed, is how I describe those. Right? Like this one's being pulled in these two directions. This one's being pushed down, and there's like stress on these springs or whatever that I've got. I don't know. I'm trying to think of a way to describe that, but that's good enough. So let's do a problem regarding clues, and I think we're done. Example. Let's see. Write the equation of the hyperbola with the following facts. With the center at 3, -1. Focus at 3, -4. And eccentricity 3/2. So let's figure out what facts I know. I know the center, so that's good news. That's always a helpful one to know. I know a focal point. So if I want to find the distance of C, length C, I could find that by finding the distance between those 2 points, right? From the center to a focus, or foci rather. No, it was focus. It was singular. I always mix up my plurality of things. So little c would be the distance between those two. So that would be the absolute value of -1 minus -4. Or you could do the proper distance formula, whichever you'd like. So that's absolute value of 3 or 3. So that's the value of c. You could actually find the other focal point if we wanted by, looks like this, subtracted 3 from the y-coordinate. So if I added 3 to the y-coordinate, I could find the other one. 3, 2 is another focus. But I don't actually really need that, I don't think, to find the equation anyway. Let's see, I know c. What else do I know? I know that if eccentricity is equal to c over a, well, I can plug in what I know. E is 3/2. Let me do that in orange, actually. 3/2 equals c is 3. Could I solve this equation for a? This one, in this case, it's maybe a little obvious. But I could cross multiply. So I'll have 3 times a is 3a. 3 times 2 is 6. And then divide. In case it wasn't as obvious. And I'll get a equals 2. So I've got C, I've got A. How can I find B? Yeah, A squared plus B squared equals C squared. So we'll plug in what we know. So that's 4 plus B squared equals 9 when I square those things, right? Subtract 4. B squared is going to equal 5, and then I'll root both sides, and I'll get b equals the square root of 5. So, do we know which way this is oriented yet? And how do you know it's vertical? The h's are the same, the y's changed from the center to the focus. Sure, so it's vertically oriented. Right? Good detective work there. So let's plug it in. So I'll have y plus 1 all squared. Y is my positive fraction. I'll have x minus 3 all squared for the numerator of my next fraction. For my denominators, 2 squared is 4 under the y, and root 5 squared is 5 under the x's. So there we go. That would be my equation. Not too shabby. That's kind of the basis of what we're doing today. You're pulling clues together, analyzing your facts, and trying to narrow it down to a single equation. But you've done that before. It's just now our facts happen to be a little bit different, and we're talking about hyperbolas. So not that bad at all. You know what? Let's do one real quick one of a rectangular hyperbola. I realized I didn't actually graph one. Let's graph the following. Xy equals 25. Let's do -25. Why not? So, let's see. Because my C value is negative, which quadrants does this live in? I think it'll be quadrants 2 and 4. Right, so it'll be one of these ones. And now let's find some vertices on it. So to find the vertices, I'll have let's see, so to be in quadrant 2, I'd have to go left, so it would be negative square root of 25, comma, positive square root of 25. And the other one would be positive square root of 25, so right that amount and then down that amount. And then clearly if I reduce these, I'll get negative 5, 5, and positive 5, negative 5, right? So let's graph this. Let's see, can I pull up a quick... Let me just delete these, but bam. There we go. Nice clean graph. Voila. And let's see, so let's plot some points. So I'll have left 5, up 5, right there, and right 5, down 5, right there, and I'll have a, whoa, man, I just glitched that out bad. Let's see if I can fix it. There we go. Problem solved. So this one is asymptotic that way, and this one. So as I get further and further to the right, this is going to get closer and closer to the x-axis and never reach it. Right? This one would eventually get closer and closer to the y-axis and never reach it. So it would look kind of like that. So that's kind of the idea of how you do that. It's not nothing too crazy. Yeah, I might remember that if my c value is negative, maybe I'll just remember that my vertices have opposite signs for x and y. Where if my c value is positive, it would have been 5, 5, and negative 5, negative 5. So the signs would have been the same. Maybe that's a quicker way to remember it. But that's the idea. So thanks for watching, internet friends. Bye-bye.